So welcome to SiLC Technology's presentation to MADIA. So MADIA, for background, is a 501c3 nonprofit organization. Our mission is to ensure the technical, scientific, and industrial workforce have the tools they need by having programs such as this on entrepreneurship, business and finance, and technology development and commercialization, all in settings which hopefully bring people together so that you can so with that, I will introduce our presenter. So Dr. Mehdi Asghari is a serial entrepreneur with a track record of success. He currently is CEO and co-founder of SiLC, his third silicon photonics startup focusing on advanced imaging solutions. His previous startups included Kotora and Bookcam, both enabled successful exits. Mehdi is one of the early pioneers of silicon photonics for the last 25 years, commercializing various technology in the space. Prior to that, he spent 10 years in the 3.5 industry, which is a different type of material, but it's still photonics, basically. So what he's talking about tonight is silicon, which is cheaper and more viable for that reason. Mehdi holds an electrical engineering degree from Cambridge University, a master's degree in optoelectronics from Heriot-Watt University, and a PhD in 3.5 integrated photonics from the University of Bath. All of that was in the United Kingdom. He has authored and co-authored over 150 journal and conference publications and holds more than 50 active patents within the fields of silicon photonics and optoelectronics. Mehdi has set up and run his own business, including this business too.
Yeah, right.
Other businesses include a small construction company, which he's still running, and a car leasing business, which he sold when he moved to the U.S. So please welcome Dr. Asghari.
Thank you. Thank you, everybody. It's a pleasure to host you here, and thank you for making time to come out here. So this is the agenda for the event, and thank you to Ruth and the MADIA team for organizing all this. So after the talk, we're going to do a lab tour for you. So it includes the facilities and our labs downstairs. We're trying to do as much manufacturing in the US. So we're going to take you downstairs and show you all the automation we are setting up and all the equipment that we have. We're trying to bring in as much manufacturing to the US and here in Monrovia as possible. So we have been taking more space in the building, and I'm hoping that over time the entire building will be SiLC. But right now we are taking about the third of the building here and with this facility. We also have some demos for you. So after we're going to break you up probably into two groups to do the tour and do it like counterclockwise to cover the whole facility. And then we will come back here and we have a bar set up with wine and beer and open bar. So we can then host you for drinks and also show you some demos of the technology and how the technology addresses different applications. So these demos, there will be an engineer by each demo. They will explain to you what the demo does and how it helps our customers achieve their objectives through real application examples. So just a little bit of logistics. Obviously, there is food there. There is drinks in the fridges, one there, one there. There is coffee at the back there. And there are the snacks underneath the island in the middle. So help yourself, feel at home. Okay, so let's see if it works. Okay, so a little bit of background on SiLC. Obviously, our location is here at the center of Monrovia. We chose Monrovia because it's a beautiful city. It's right on the 210. And I always tell my customers that Monrovia is a hidden gem and it's the equivalent of Palo Alto in the Bay Area. Because it's a beautiful city, it's really safe, and it's right on the corridor, right?
And that was the inspiration of forming MADIA, because I made that connection too. I thought this is like almost like Palo Alto.
Yeah, it really is. It really is. And every company that I come across and that wants to expand, I usually tell them, come to Southern California. I certainly in College Monrovia, and it's a beautiful city. We love it here. So thank you. So the company was established in 2018. And we started in one of John Tanner's buildings just next door and moved to another John Tanner building after about 6 months, and stayed there for about 3 years until John kicked us out because he didn't have enough space for us. And we moved here, and we're very happy here, as happy as we were with John. Of course, we miss him. The company has been very active. We are about 60 people now, and about 30 PhDs. Almost everyone here has advanced degrees, masters and BScs. And we also like to be very active in the community, so we always hire maybe 5 to 7, 8 interns. Whether you are a high school graduate or you are in the first, second year of high school, we love to show you what engineering is like. We would love to hire you over your summers and breaks and give you a chance to discover engineering. We want to help the community and the kids. So whether you are a high schooler here or whether you have kids that you want to send to us to be trained over summer or Christmas breaks, we'd be happy to do that. And of course, we pay you. So we have been very active in filing patents. We have filed about 260 patents in the past 6 years, out of which about 70 has been granted. What is unique about SiLC is the long heritage of the founders in silicon photonics. Silicon as a technology may be familiar with everybody. That's what all the processor chips are made. In the computers, in your phones, you all have these ICs or electronic processor chips. What we do is instead of making electronic chips or circuits, we make optical chips. So instead of using electrons, we use light in these chips. And the advantage of light is that it can get a lot more done much faster because it doesn't have the capacitance, the inductance, all the problems that electrons have. So we make also lasers and detectors that transmit light, receive light, all in a tiny silicon chip. And we have them on the microscope. We will show them to you. They will show you all the different components, and then we show you the devices we make with those chips. And we go all the way to system level and show you the application of how these devices solve problems for us in the different markets we are in. So all that is set up here, and we hope to show you during the course of tonight. So our unique claim to fame is therefore our integration platform, which is quite unique. It's something we have developed over the past 30 years during our journey in different companies. There is no other company in the world that has that technology. We are completely unique. We also are unique about the way we manufacture it. We have a fab in Japan that does all our manufacturing for us. They do it to our spec and to our IP. We own the IP on the manufacturing. We even own some of the equipment in the fab. So even if somebody buys one of our products and cross-sections it, tries to reverse engineer it, good luck to them. There's no fab on the planet that can make it for them. So that gives us a huge differentiation that usually only big companies can afford. For a small company like us, that's a huge differentiation. And it comes from our 30 years of heritage and knowledge. And although we are fabless, we have always had the fab in our previous companies. So we have all that knowledge accumulated. And then, of course, we have built layers of electronics, IC design, software, and system level knowledge. On top of that, we design our own ICs. So a lot of our products, we have our own ICs in them, or the laser drivers, SOA drivers, all kinds of stuff, so that we can reduce the cost, improve the performance, and optimize the size of the products. We are enabling multiple markets with highly efficient image processing on the edge. So we're basically trying to make eyes for robots. And I will talk about this in a moment with other slides, but we are talking about the age of AI, artificial intelligence, machine learning. Somebody said, I wish AI could actually do my laundry and clean my house, so I could do painting and arts and so on, rather than the other way around. I don't want to be washing my dishes and cleaning my house while AI writes my poems for me and does painting. So we want to enable that, right? We want to enable you to have robots that does everything for you. And if robots are to do that, they need to see. A dumb blind robot is not able to do as much as a human can do. So, but the technology from a computing perspective, from a robotics perspective, is there. It can do it. What is missing is the vision. And that's what we're going to enable, and I will explain to you why the vision capability today is not good enough and our technology is needed. And the applications are huge. We are currently focusing on perimeter security, industrial and robotics, and mobility. And I will explain these in more detail later on. Okay, obviously any startup like us needs money to survive, and a lot of our money comes from venture capital. Some people in the room are actually small investors in us, and we're very delighted to have them. And we also like to welcome the community to invest. So if anybody wants to even write a small check to invest, we welcome them, even though it's quite a lot of administrative work for us. But we do allow people to invest so they feel like they have a stake in the company, and they all try and help us. But we have some large investors, which includes Honda, the automotive manufacturer. They invested in us recently, and we have a very big project going on with them, confidential. We also have Sony and invested in us. Sony is big in imaging, and they are one of our major investors. We also have Epson, which is you know them for their printers, but they're also a big robotics company. So they also have invested in us. Rome, you may not know, but they're a very large semiconductor company in Japan. They're also an investor in us. Yamato is the equivalent of FedEx in Japan. They have also invested in us. AMS Osram is a large technology company in Germany. They have invested in us. And Hankook is a tire guys from Korea have invested in us. And these are customers. So almost all our customers end up investing in us, because during the process of working with us, they increase the value of the company. And by investing in us, they can share some of that value back. By our share price going up and the value of the company going up, they'll be able to claim some of that value back that they give us by working with us. We also have Dell as an investor. They led one of our rounds. They're a board member, and Alter is also another venture capital investor in the company. So our board is completely independent. It's not linked to any of our customers. And our board is completely US-based, and we are a completely US-based company. Feel free to stop me at any time with questions, but we will have time hopefully at the end of the question. Okay, so what is the motivation for what we do? There has been a steady reduction in fertility rates. We can see this here in this graph. It's quite scary when you look at the drop in the fertility rate, especially in the Western world. In some countries, the fertility rate is scary. So in Japan, South Korea, the fertility rate is less than 1. You need about 2.1 to regenerate the same population level. A couple need to have 2.1 children on average so that the population stays the same. In the US, it's about 1.5. In Japan, it's like 0.7. So the population is dropping drastically. And it's very hard to also encourage immigration to bring people from abroad, because the culture of the country changes and all that. And some people don't have the training necessarily. So it's a big challenge for all societies. And the only way you can address these, together with the aging population, also means the working age people are dropping out. So especially after COVID, we had the baby boomers, a whole bunch of them retired. I heard many people here in this room say, I retired. So that's a major problem also. And also a lot of us want to work from home. We don't want to go in an on-air condition warehouse, and a lot of the nature of the work is no longer desirable for a lot of us. So there is a significant shortage of labor, and that's driving the cost up, and many industries just can't do the job they need to do. So there is huge push for robotics and automation across many, many industries. And you can see here the growth predicted for robotics industry. And when I say robotics, it can be robotics for warehouse automation, it can be robotics for manufacturing, self-driving cars to us count as robotics, drones that fly around, which is the counter UAS part, which I need to explain later, that's also robotics to us. So when we say robotics, we mean machines in general, anything that wants to control and have autonomy by itself, we call robots. So it's really an industrial revolution that's going on. Now, what's the problem? You talk about, you can say that, guys, we have been automating factories for 50 years, for 100 years. What's new? The new is the autonomy part. Yes, we have been automating factories, but these jobs that machines did were highly repetitive. They were in a controlled environment. They did things that were dictated beforehand. There was plenty of power available. There was plenty of computational capability available. What we want to do now is let machines loose in our environment, on our streets, in our homes, let them interact with people, potentially endanger people's lives. And we want them to contribute to our GDP growth and do the jobs we do, not the repetitive jobs that they used to do in the factory. So there's a huge difference there. And for that, we need not only AI and robotics, we also need vision, because that's the only reason why we can function with the level of dexterity and efficiency that we do. And these devices also need to be highly mobile and power efficient, and they otherwise they won't be able to run for very long, and they need to be connected again to charger. Now, the current systems that we have are basically the camera-based, or some 3D systems are coming up which are LiDAR-based, but they all have issues. One of the most, the biggest challenges they have is detection of motion or velocity. Now, we don't often perceive that we see the world as a moving world, but in reality, 90% of our vision is actually associated with detection of motion. It has been critical to our survival as a race. And majority of animals actually see moving things. So if you remember from the dinosaur movies, they say if a dinosaur comes, freeze, right? Or if you see an animal that wants to eat you, freeze, because if you are freezing, they don't usually see you. So most of the vision of animals and humans is catered toward detection of motion. In our eyes, we have about 90 million rods which detect motion, and about 5 million cones which detect color. So 90% of our vision is black and white, and detects movement, and only 5% is color, but the brain adds the color to everything. So if you see something move, you immediately run, but you don't even know what it is. And that's the motion sensors. When you drive the car, it's the motion sensors in your eye that work with your muscles directly, because the brain is too slow to help you drive. When you play sports, play badminton or tennis, it's your eyes working with your muscles directly. The brain is not really playing much of a role there. So what we are trying to do is enable that hand-eye coordination, that ability to have that level of dexterity and efficiency that we have and current robots don't have today. That's why when you see movies about robots, they move, they stop, they move, they stop, because they don't have that hand-eye coordination and dexterity. So right now, a robot is only about 10% as efficient as a human. We want to make the robots as efficient as a human. And there are other challenges like environmental challenges, lighting conditions, and multi-user interferences, and there are many, many issues. One of these self-driving cars that you see around the streets, not so much in LA, but a lot more in the Bay Area, you don't realize how much computation goes in there. These things are extremely power hungry and computationally intense. Cameras also have a lot of issues with lighting and so on. So a LiDAR, the kind of LiDAR we make, is critical if you want to get these things widespread and deployed everywhere. Motion. Why is motion so important? So as I mentioned to you already, 90% of our vision is associated to motion, as is with other mammals and other animals. And it's really for rapid identification of potential threats. If a tiger jumps at you, you run before you know whether it's a tiger or a cat or anything else. When you play sports, same thing. And that microdoppler, which is the movement of the individual components of the body, like your arms and hands and legs moving, like you see here with this person, it also helps us with identifying what the object is. But a human being or a cat or a dog all have different microdoppler signatures. So the movement also tells us something about what the object is. That's very important. And then predictive, precise, rule-based reactions is what gives us hand-eye coordination. So that's why we can shoot ahead of the duck. That's why we can play badminton and sports, because you're able to predict where the ball comes, even though you don't really see the ball very clearly. So these are all very important. And the only technology that enables that is coherent LiDAR, which I will explain in a moment, which is what we are doing. There are other technologies, but none of them can provide this information on velocity and motion and microdoppler. However, these systems are very complicated to build. And without a suitable integration platform like the one we have, they are not going to be cost effective. So they have been built for maybe a decade or two, but systems will cost hundreds of thousands of dollars, and they're usually huge, and they can only be deployed for military applications or mapping and so on. What we are trying to do is make that very cost effective, small and compact. Again, feel free to stop me at any time. Okay, so there are two types of LiDARs or 3D imaging, 4D imaging. One is called time of flight. The other one is called Coherent, Doppler, or FFCW light. I apologize if it's getting a little bit too complicated. I try and explain it in a way that is generalist. So time of flight is basically like echolocation, what basically bats have, right? You send a signal, you wait for the signal to come back, you know the velocity of the light or the sound or whatever you are emitting, and you measure the delay and you say, okay, it took 2 seconds to come back, hence the object is so far away, right? That's how usually people say, you know, lightning, they calculate the how far away lightning is by measuring the distance between light and sound, something similar, or what bats do to see the world. So you basically, it's based on emitting a signal and calculating how long it takes to come back. That can measure distance, and it's relatively simple to do, uses the standard components, but the precision is very limited, and it doesn't give you velocity directly. The better way to do it, and the only technology that can give you velocity or motion information, is the coherent LiDAR. What you do with the coherent LiDAR is you don't send a pulse, you send a continuous level of light, but you chirp or change the frequency of the light or the color of the light by a tiny amount. By the time the light goes to the object and reflects back and comes, it's now at a slightly different frequency to what you're generating on the chip, because you have been changing the color continuously during that time, or the frequency during that time. So what comes back is a slightly different color or frequency to what you have. Then you beat these two together and you measure the beat frequency. The benefit here is that, like sound, which reflects off objects, you get a shift in the frequency or the sound of the sound, right? When an ambulance comes towards you, the pitch changes, versus when it goes away, it's because the sound changes based on motion. Light is the same. When you reflect light off an object and it's coming towards you versus going away, the frequency of the light changes, i.e. the color of the light changes by a tiny amount, which we don't perceive. We don't see that because it's too little, but our circuits can calculate that. So when we shine light on an object and it's moving, the color of the light is changing a tiny amount. And our technology allows us to measure that tiny change in the color of the light and tell you how fast the object is moving, either away from us or towards us, by that tiny change in the color of the light. This technology allows us to do that, and the optical circuits we make can do that, and that's why they're complicated. They also have to be very high performance, because the frequency of the light, as you know, is very fast. It's terahertz. The wavelength of it is in micrometers. So these circuits have to be extremely high performance and complicated. So that's what we do. That means we can not only measure how far away objects are, but we can actually calculate how fast they are moving. And we can even calculate the relative motion of the different components of the object. So we can calculate how fast they're moving, but we can also calculate how fast my arms and legs are moving in relation to my body. Or we can calculate a drone as it's moving and calculate the velocity of the propellers very accurately. And I'll show you examples.
I'm a little confused. You're continuously varying the wavelength that you emit. And then you're trying to actually look at the variations in wavelength that are returning to you.
That's right.
How can you kind of like reconcile the two? Is that you've got like two variables. So when you're trying to, I can understand how if you had a fixed wavelength of light and it was coming back slightly different, you could then compare it to your reference. But if your reference is constantly changing.
So the reference is changing in a linear fashion. It's a very constant linear fashion, and then we take it off, and then we bring it down, and we do sawtooth. So we have two unknowns and two equations. So we added. So there is two frequency on the way up and the way down. The frequency difference, and we also have depth and velocity. So based on those two unknowns and those two equations, we can solve the problem. Maybe I can explain it to you afterwards.
Okay.
It's fairly simple math, but you're right. You need actually two chairs, not one chair.
Okay.
You need the up and the down. Otherwise, you can't solve the problem. In fact, we do three sometimes. All right, so it's a little more complicated the way we do it, but it gives you a lot more information and it actually is far more accurate. Usually we can offer 10 to 100 times more accuracy than this other technology. But in exchange, the technology is very complicated and you need the kind of integration we do to do it. Otherwise, the systems are not practical.
With the increase in complexity, do you also have an increase in the data rate that you have to move around as well?
Oh, that's a good question. Yes, we do. Yes, we do. And that is why we also design all the electronics and the DSP, and there's a lot more algorithmic stuff because you have more data and you create also. But what we try and do with FMCW, our LiDAR, is reduce the frame rate and reduce some of the resolution that machines don't need, but increase the accuracy. So we try and optimize the solution to the application and the customer. We humans want to see very high resolution images because our visual is spatial. With machines, they actually see differently. So we need to cater what the machines want to see. And if a human sees that image, they may not make much out of it. But to the machine, it's exactly what the machine needs. So just a little bit more on the value of velocity. I mentioned already rapid identification of threats, classification based on microdoppler, the motion, and ability to do precise rule-based reactions. I just want to highlight those here. So ability to detect threats right away. So when something is moving, this was actually done outside our previous facility, John Tanner. There is a car park, there are trees, and there is the ground, and we had one of our engineers cycling in that area. You see the cyclist immediately. He's moving at about 3 meters per second. You see his legs. You see these little white dots? These are his legs as he's pedaling. You don't need to do any image processing. You see it immediately. You don't have to go through all the layers of perception processes and spend many cycles and frames. You see it immediately, which means you can react immediately. That's how we see the world. We see the motion immediately and our eyes communicate to our muscles immediately. That's what we can do with this technology. You see the movement immediately, you react to it immediately. The brain, which is the electrochemical process, is too slow. We can do that right away. Now, microdoppler. If I see something with a camera or with the current technologies, I don't know what it is. I have to go through boundary conditions. I have to analyze it. I have to figure out it's an object first. Okay, then what is the object? If a bicycle is standing, it looks one way. If it's lying down on the floor, it looks a different way. So if I see a dog from one side versus the other side, it's different. However, the microdoppler components of how the arms and legs move is a unique signature for every creation, every animal, every being. And you can use that immediately to say what things are. For example, we use that to identify a bird versus a drone. The way I will show you more examples here, but the way the bird flips its wings and the way the drone, the propeller move are unique. You don't have to go through many layers of perception to say this is a bird versus a drone. That's a huge help for machine perception, AI models, and so on. Okay, so a little bit about our technology. As I mentioned, we basically integrate all the complicated optics you need in a silicon chip. We use wafer fabs that other people use to make electronic devices, to make our optical devices. And we can put everything we need from the light source that generates the photons and the light, to detectors that detect it, and to all the other processing devices in a single chip. And you will see them on the microscope, and you can ask questions about what they are and what they do. And our technology is quite unique there. And we have about 10 to 100x better performance on some key performance metrics for this application compared to our competitors. And that's why some of our performance is completely unique, and why companies like Sony and Honda and others invest in us. Our product is called Ionic, which stands for bionic eye. That's the eyes for the robots. It's the only product on the market that's fully integrated. It's the smallest product on the market. and the only single chip product on the market is really years ahead of our competitors. And you will see it during the tour here today. We offer it in different varieties. Now, Ionic generates multiple layers of information. One is depth. We tell you exactly how far away everything is. Every pixel in the image or every dot in the image has a depth information. So you know precisely how far away it is. And the depth information is very accurate, about 0.01% of the range. We give you velocity information, which is how far away objects are, as well as microdoppler, which is the relative velocity. We also give you polarization information. Polarization may not be a general topic for everybody. So polarization, light travels in two components, horizontal and vertical. And that's really important. For example, most of your glasses, sunlight glasses are actually polarized because the light that reflects off the snow gets polarized. And that's very important information. So most materials change the polarization of the light, and this information can help us identify what materials are made of. So for example, this is wood, this is metal, this is plastic. We can use that. And then of course we can add color. We can add a camera and add color information. Okay, what happened? Okay, so some of the attributes of the technology, we can also change the wavelength. We can also give you broad spectrum imaging. This is becoming really hot and really cool these days. Everybody wants to do broad spectrum imaging, which means like a spectral analysis. You want to know what is, if you take an image at different wavelengths and you look at it, it gives you different information about the objects. So we can do that. We can also do polarization imaging, as I mentioned to you. We can basically identify what materials are made of based on that. We have the ability to achieve very long range. This is world record. I think we hold a world record by a factor of 5 compared to our competitors. This is Mount Wilson. You can see the power, the towers on top of the hills. Any nice bright day you look, you will see those. And we have our zoom camera out and we're taking an image of it. You can see just barely the image here. And this is the LiDAR image of that. So we can actually distinguish the range and the exact features. So I think the closest our competitors can get to is about 1 kilometer or so. But we actually demonstrated 20 kilometers recently.
Does the smog interfere, the LA smog?
It does. Yeah, it does reduce visibility. So
it could be even longer if you were in a different place.
It could be. Yeah, exactly. So clouds, rain, they do limit our visibility. A clear day is clearer, exactly.
Man, is the blue and green a distinction of the distance between the two towers?
Look bad here?
No, on the tower.
Right. Oh, yeah, they are. Thank you. They are, exactly. So the scale here you don't see, but it actually shows that these two are about 6 meters away from each other or something like that. And it's amazing. The resolution we have is really precise. So this is range, and yes, the color is distance. Thank you. Very good. But it's amazing that you can actually even see the structure, the stars, and everything. So we actually, one of our defense customers asked us, can you see a power line at 2 kilometers? And the team, we did the test over the weekend. We could see power lines at 5 kilometers. So a tiny little cable, we can see that 5 kilometers away. You don't see it with the camera. It's really hard to see.
So it can't go through a cloud, like LiDAR is not good for cloudy skies, or?
It's hard to see through the cloud. Radar can, and some other frequencies like the blue that our colleagues who are visiting us can see through clouds. That's why we are here to discuss that. So certain frequencies or wavelengths of light are better for certain applications. Blue wavelength can see through water, can see through clouds. That's why we're looking at that technology and that color. Our 1550 wavelength, which is a different wavelength, is not so good for through clouds and so on. The penetration depth depends on how dense the fog is or the cloud is.
But your technology can be tuned to those other frequencies?
Yes, they can. And that's why our colleagues are here to discuss that. So you can see through clouds. We can see through smoke. We can see through fire. We can see through not so dense fog. But if the fog is really, really bad, or if the cloud is really dense, then it's hard to see through it.
What's the limiting factor on your resolution must be your timing technology.
That's a
Like
good question.
how, you know, otherwise you can't different, it's like resolution.
Depth resolution.
Yeah, I mean, if you kind of got like picosecond or
Right.
or finer timing.
Yeah, it's usually the,
What's the sort of, what is the limit, at 11 kilometers, what's the like minimum?
resolution and depth.
Yeah,
Yeah, that's a great question. So the frequency shift we apply gets a bit frequency back, right? The bigger the frequency shift we apply, the higher the resolution we can have. But the longer the range is, the bit frequency gets even higher. So that means the bit frequency you have becomes very, very high. So to get this, we are using a 5 gigahertz bit frequency, which is really high. We are using a state-of-the-art FPGAs with 5 gigahertz bit frequency to achieve this. It's very hard to achieve, to have anything with higher than 5 gigahertz ADC. There is a new one coming with 8 gigahertz ADC. So that's what's really limiting us, is the ADC speed with how fast you can digitize the information. That's a good question. Now, on the other range, this is 11 kilometer range, a few meter resolution. On the other hand, we can actually measure your heartbeat while you're sitting down. We can actually say, yes, you're breathing and measure your breathing, or if you hold your hand up, we can actually see your fingerprints. Nothing that you're doing, we're not doing anything on the biometric side. We don't want to get into that kind of application, but the technology has the resolution to resolve micrometer level precision and do that kind of precise measurement. Here, if you are measuring the heartbeat of somebody who's sitting down at 5 meters away, and you just see the motion, the movement. Okay, applications, many applications. Industrial robotics is one of our key targets. Smart infrastructure is another. These are fairly large markets. Autonomous and mobility is another reason why Honda invested in us, and we're really excited about Honda because they don't just do cars, they do trucks, they do planes, they do robots, they do gardening equipment, they do marine, and so on. So we're really excited about that collaboration. And we also do some applications on consumer and mobility, and I will talk about this a little bit.
Are you working with the Sony Honda collaboration projects, or are you working with them separately?
We're working with them separately. They each know that we could eventually collaborate.
Right, well.
But we haven't connected the dots. Sorry?
They have a big partner.
They do,
Yeah.
They do. And it's a good thing that we are connected with both of them, and they talk to each other and we talk to each one of them, but we haven't yet created a triangle here because it's a bit too early.
Yeah, understood.
All right, so we talk about some of these collaborations in these markets. We have a huge range of customers in each market, and so we have more customers than we have time to deal with, and that's why customers end up investing in us, because they're competing for our attention. So if a customer invests in us, the more they invest, the more attention we give them because we just don't have time. So they all end up investing, and they say, "Oh, I want more attention from you." We say, "Well, get your checkbook out." So they usually then have to invest again to get more attention from us. But the higher up the people are in this list, the more collaboration we have with them. We are also active on the government side. We've created a lot of relationships. In fact, JPL is one of our big collaborators just down the corner. We do a lot of work with JPL. High Point Aero is now called Design. We do quite a lot of collaboration with them on detection of drones. We are also working with US Air Force and Navy research labs. Okay, the three key markets for us, one is manufacturing, logistics, and warehouse automation. Our first product here is called Ionic Trace. You will be able to see it on the display here, and you will see a demo while you walk around and hopefully drink some beer and wine. You will see those demos. The other one is called Ionic Horizon. This is a product that we are doing for US Air Force, but the applications is dual use. So it can also be used for airports and commercial applications. This product can see drones 2 kilometers away. The hardware has the ability to see drones 5 kilometers away, but the software needs to be optimized for 5 kilometers. So within a year or two, we will do 5 kilometers for those guys. And then mobility is the R&D work we are doing with Honda that will hopefully kick into action by about 2028 to 2030. So some of the applications here, so our technology can go down to micrometer level depth precision measurements. That's where we can bring fingerprints and we can do inspection. You can see here that the range accuracy can go down to about 3 micrometer, i.e. 10 times 10 to the minus 6 of a meter, at about a meter or so. So we can measure that accurately at a meter away. This is like your fingerprints are usually about 50 micron or 100 micron. So it's way, way below that. And the precision is a fraction of a micrometer. So it's really very precise. The tools that you have to buy today to do this kind of thing are like equipment like this is huge. And we want to make it into something tiny that you can put on top of a conveyor belt or carry around with you, so you can have that level of capability from a tiny, much more smaller, more compact device. The other one that we are really excited about and working with some really large customers is warehouse automation, logistic automation. And here you want to have a range of millimeter at 10 meter or so. And again, we have a highly differentiated product. That's the trace. You will see some of these images as you walk around, like water bottles, drones, cans, and so on. You will see the images we create. Here, the customers want to measure dimensions of objects. They want to see defects. Is the cap on the water bottle or is it missing? Does it have a dent in it? Does it have a scratch on it? So that our vision system will enable them to do that. And then they can measure the sizes of the boxes and crate them and put them in trucks and so on. So automates logistics. So that's a big differentiator, and we have sub-millimeter precision. Another application is airports and airport management. One issue is when airplanes land, you actually, first of all, you want to avoid accidents. You want to know what height they are, how fast they are approaching the runway, guide the airplanes to land at the right height and the right distance and the right speed. And our technology can do that. And the other one is flight manifests usually don't have the accurate information about exactly what that plane is because they change them at the last minute. And the landing gear, like the runway they bring to you or the fueling, they all are different for every plane model. So if you know the plane model, precise model, 2 minutes earlier, you can cut 2 minutes of the stoppage time. And that's worth a lot of money to the airports. So our systems are being deployed. We are working with customers to deploy our systems in airports. We are working with one that has 80% market share of worldwide airports. They provide services to the airports. The other issue is damage to jet engines. There are a lot of luggage handles, that come off the luggage as people take the luggages out of the plane and put them in. There are all kinds of bolts and nuts and tools that are lying on the floor, and they have to be inspected manually. We are automating that so that you can actually pick up a luggage handle or bolts and tools at 100 meters away. And there is no one else in the world that can do this. We send this to our customer, and they were amazed that we could actually see luggage handles 100 meters away. You see this here. You don't even see it with the naked eye or a camera. So this was quite amazing. And that is where the polarization capability comes. When you have changing directions and angles, polarization shows up. So this is quite a unique capability, and you're working with somebody who has 80% market share in all the airports in the world. Another one is a smart infrastructure. We have the ability to monitor the roads, tell you if there are cracks, potholes, other bits and pieces there. The traffic management, trying to measure the flow of traffic without intruding on people's privacy. These are very important. The next video I will show you shows this in a little bit more detail. So here we are mounting our systems at top of a hotel a kilometer away and looking at traffic at a distance of about 1 kilometer. You see the power lines are about 1 kilometer away. You see the motorbike here at about 880 meters away. There's a truck coming back. You see that this truck is about the same. And you zoom in, and you can actually zoom in on the motorbike, and then you zoom out again. So you are able to monitor the flow of traffic you can then zoom in on any object you want and precisely calculate the range and velocity without intruding on people's privacy.
So when I was looking at this stuff before this presentation, I thought that isn't very meaningful to me but it's not intended to be meaningful to me. It's a computer that has to understand it.
Exactly.
So
Exactly.
a human doesn't monitor that, a computer does.
A human, that's right. That's right. So for a computer, usually about 7 or 8 dots on object is enough. But humans usually need a lot more than that to say what it is, right? So it is a challenge for us to make something meaningful to our audience,
Right.
while our customers don't really need the same level of resolution.
What type of resolution of visual field do you get? Like X by Y? How many dots?
That's a great question. That depends on the application. So each system has a certain level of capacity. So a single channel system at short range can usually give you about 1 million pixels in an image. If you wanted to have 10 frames per second, then that will give you 100,000 pixels per frame. The LiDARs that we make for long range, they have lower resolution, but they have higher range. But those systems have 16 channels. So they have 16x the resolution. So those usually have a couple of 100,000 pixels in each image. And then once you decide your field of view, you can then decide how close you want the pixels. So it all depends on how you optimize the system.
Sorry, one thing. The system seems inherently capable of measuring distance coming and going away from it.
Right.
But what if it's traversing perpendicular to its field of view?
So the distance you can
How does
measure.
that affect the assessment of velocity?
Yeah, that's a great question. So tangential velocity, there's no Doppler shift.
Yes, exactly.
So the only Doppler shift you get is because the objects never go around the perfect circle, right? So there's always some movement in the radial direction. And if you go through the math, you are able to calculate the velocity shift from one end of the object to the other end of the object as it goes around that a straight line or whatever. From that, you stipulate also the tangential velocity. So there are ways to do that.
How much more complicated would it be? Is it possible to add a thermal component to this?
Oh, a thermal camera. Yeah, so we don't do that, but our customers do. Our customers usually add radar,
So they
thermal
can
camera,
layer it.
IR camera. Yeah, exactly. So you could argue our detectors are kind of thermal image, but it's a kind of
It looks
infrared.
very similar. but
Right,
it's-
exactly. Yeah, that's right. Okay, so moving on to drone application. So counter UAS, means counter unmanned aerial systems. So basically drones. We want to detect drones. Drones are becoming a menace. They are an issue in war and also civilian applications. There are significant risks to our critical infrastructure. People can use drones to stop airports, prison breaches, border breaches, all kinds of issues. So we have many customers we are working with on drone detection, drone tracking, drone classification, and so on. And what you have to do here really is to detect, track, classify a drone. You need to then find a way to defeat it or mitigate it. And you need to do it without any interference with civil life. It's no good if we detect a drone and bring it down, but in the meantime, we fry everybody's Wi-Fi, right? Or all your cell phones. That's no good. So we need to do it in a way that we don't disturb your life. And we also need to cope with highly dynamic, complex, diverse environments. Where there are, in a city, you have so many other stuff going on. We need to be mindful of that. But it requires very complicated systems. So what are the existing systems? Existing systems that our customers have usually consist of radar and different types of imaging systems like thermal images or infrared images or visible cameras. But these systems all have their own problems. So for example, a radar usually gives you very low resolution image, and the image is really of what they call radar cross-section. For example, a bird has actually a higher radar cross-section than a fighter jet because of the way the fighter jets are designed. So a can of Coke next to a human will have a much bigger signature image than the human does. So if you have a can of Coke next to you, you won't be seen by a radar. It would focus on the can of Coke. So radar has its own great advantages, but it also has many disadvantages. So to see a drone at a kilometer away, if the drone is hovering against trees or mountains, you won't see the drone with a radar. But it's great to see a drone in blue sky 5 kilometers away. It detects something is moving, but it doesn't know what it is. So that's basically what the radar does. It's first layer of detection. Cameras are very good for visualizing things. But again, I have a drone in every little red square here, but maybe only about 20% of them can really be detected by you or a visual system. So it's really hard to do, again, depending on lighting and contrast. Cameras can be effective or not effective. Again, cameras are usually used as a first layer of detection, but they work well against a very clean, clear background, not complex background. So we need a layered vision system that consists of radars and electro-optic cameras, but LiDAR adds a lot of value there in terms of first detection, tracking, classification, identification, and mitigation. So that's how it works usually. So we basically get a signal from the radar that tells us, hey, I just detected a signal, although I lost it, in that coordinates in the sky. We then focus our LiDAR in that area. We start with a wide field of view, but has low resolution. As soon as we detect it, we narrow down the resolution, the field of view, and we get a high resolution image so that we can have an image like this. This is too much. The machine doesn't need this level of resolution. We deliberately did it like this so we can see it. But you can see the propellers, you see the red and the blue, because one side of the propeller comes towards you, the other side goes away. So one is red, one is blue. You can also see the rotation. You see the rotation, sometimes it goes green, sometimes it goes orange, because the drone itself is rotating. So this level of resolution, even less than this, helps the machine to identify, is it a drone or is it a bird? And if it's a drone, what type of drone it is? Because each drone has a different motion signature for the propeller. You could even code your propeller motion with some information so that you identify this is your drone based on that coding you put in the propeller. So it's very, very powerful.
What are the power requirements? Can you put your sensor in another drone, or do you need a lot of power and therefore a lot of weight?
Depends on the application, yeah. So you could put a sensor in a drone, but you are not able to do 2 kilometers with that sensor. Those 2 kilometer systems are quite big and bulky. A drone, unless it's a huge drone. Yes, an airplane can carry it. Some of these big drones can carry it, but a tiny little drone won't have enough power to do it.
Wait, does it the same signature apply to fixed wave as well as rotary wave, or is it drone specific?
So it will be dependent on the signature is the signature of the propeller, right?
Yeah.
So depending on the angle and how it's mounted, you will see it in a different perspective, but you can still calculate the rotation. Yeah. And the signatures are very different, right? I'm showing here the signature we get from a drone versus a bird. And I don't want to go into the details of it, but you see how a bird signature in motion is different to a machine, to a bird. So this is a bird, this is a drone. For even we can see that difference. But for a machine, a learning model or AI, this is just very simple to detect.
It seems to me that this all requires a lot of data capture. So how do you handle all that data to then be able to come to the conclusion that this is a bird or this is a drone or whatever?
Our products have a DSP chip inside them. So our products have a DSP chip or a FPGA inside them that does the processing right inside the sensor. So it's the same like our human eyes, right? Human eye does some level of processing of the image. We don't send image to the brain, right? We process images, we send it to the brain, then the brain reconstructs it. We do the same thing. We process the image, we send in the image, the processed information to the AI, and the AI then reconstructs what it needs from that. So all that processing happens inside our sensor so that the bandwidth we need is limited. We only need hundreds of megahertz of data to be sent to the machine. Otherwise, the data handling we have is gigahertz of level of data, gigabits of data inside that LiDAR. But outside LiDAR, we only communicate megabits of data because we do the processing inside. Very similar to how the brain does it. So we were at the show recently, and the US Navy came and said, can you see a ship at 2 kilometers away? Because radars don't give high resolution images. They also struggle with reflections of waters and so on. And we went back to our hotel room. We took one of our systems with us, and we actually took an image of one of their ships as it was porting into the San Diego port. And this is 2 kilometers away. And you can even see the tugboats that were pushing it in. This is the actual resolution or the actual focused image. You can barely see the tugboats or any of the details, but you can actually see the tugboats very accurately. You can see the mast and so on. So it's quite remarkable the level of resolution you can get. Again, we wanted to look at the power lines, as I mentioned. So you can see the power line is about 1 kilometer away. We did some tests over the weekend, which we could do actually 5 kilometers. A lot of features you can see. So this can be used for mapping and so on. I mentioned this already. I just wanted to make sure you see the bigger image of it. So you can see the camera, even though this is a high zoom camera, is actually, we can actually get a lot of details from this as close to the high zoom camera. Automotive, why did Honda invest in us? Because we are the only company that can actually see a tire, even though tire is only 3% reflective, at 150 meters away. These are tests we did for them down here. The can of Coke could be seen next to a highly reflective object or a low reflectivity object to a highly reflectivity object. This is the problem for many sensors. High reflectivity objects bloom and saturate a small object next to them. You could see somebody running around. This was tangential. So you were asking about, can you see somebody more tangential? The answer is yes. You see the micro Doppler. You see the yellow, the green, the blue. So you actually see somebody is moving. Same thing here. This guy, Prakash, is actually running behind the car and is tangential, right? And yet we can actually see him. You can see the blue and the red, and you can see him through the window of the car. And for a camera, it's almost impossible to detect that and perceive that it's a human. But with us, as soon as you see a red or a blue, you know it's something you have to brake the car. Because it could be a child behind the car jumping in front of you to get the ball that they're running after. So you can immediately stop the car to save somebody's life. And if you are able to react 250 milliseconds faster, you have an 80% more chance of saving somebody's life. 250 milliseconds is not a lot. So if you have to go to another frame of an image of a camera, you've lost it already. So you really need to be able to do it all in one frame, and that's what we enable, instantaneous detection. That's why Honda invested in us, and we're working with them. Some other fun applications. I'm not going to go through a lot of details. I'll just show you a couple of movies. So we also are doing work on the space. As I mentioned, our collaboration with JPL. We also are working with a couple of other space companies here in the US, in Japan, in Spain. We are also working with motion capture. We actually did a movie here, and we got some interest from Hollywood. We didn't follow up on it because the volume wasn't very high, but it's certainly interesting. I'll show you a movie here of what we did. And we're also working with companies on sports and health and wellness. And here we're basically doing motion analysis of athletes as they move, as they do things. You'll be able to analyze their motion and what's happening with the body.
So this technology is being used over, phenomenal range of different products. In terms of system integration, how much of that do you do here? Like, do you have a universal API, or does each vertical have its own API? Like, how does that happen?
Yeah, it's a great question. So for certain applications, we vertically integrate all the way to the end. For some other applications, we let our customers take over. When we see adequate interest from a broad range of customers to vertically integrate to a final product, we do that ourselves. In other areas, we work with system integrators. When we don't have the end application knowledge or it's just too much for us, we'll let them handle it.
So for example, in the factory automation, there's a number of sort of backbones for system integration. Are you working with the sort of typical CAD/CAM?
We are working with a couple of major players in that area, with probably the three out of the largest five. But we are also developing our own vanilla flavored product, because we have so many customers come to us and say, we don't have the resources and the knowledge to do something. Can you do it for us? And we said, sure. By the time we see that the level of interest reaches a threshold where it's justified commercially to do a product all the way to the end, we do it.
So is that like, in terms of, you were talking about like, not having enough time, is it the system integration that is the big limiting factor for you, or is it more on the hardware side?
It's everything. It's everything. So every system almost requires some level of customization, and you go through the silicon run, and then the interface can be very time consuming. The software, coding, and all that. So it takes about 2 years to develop a product. It's a lot of effort. So just let me cover a couple of examples. Motion capture. This is a big industry in Hollywood here. We wanted to show the motion capture capability. At the moment, if you want to do motion capture computer graphics, you have to wear these special suits. You have to wear, if you want to do facial kind of posturing, you have to wear even more complicated stuff that puts laser beams on your face and stuff so that you can see the facial features. It's really hard to model, for example, hair and the flow of the hair and so on. So it's really hard, and these things have a habit of dropping off, and you have to repeat again what you did. So, and these systems are very expensive. The cheapest is a few $100K, and the good ones are millions of dollars. So it's really hard to do, but we can do that with our technology. So for example, we had a lady come here and dance in our kind of facility over there. And then we use the point cloud data from her motion to create a computer graphics image of her. This is a character that called SiLC that we created for our marketing activities. And SiLC is supposed to have Silk's vision, and it's supposed to see things much better than other robots can. And then from this, we created this movie that I will play here for you. So that's the lady dancing, but the dance is transferred to SiLC, and then we create the background, all computer generated. So she's dancing here, but you see the SiLC dance on top of a roof next to a swimming pool.
So how dense was that point cloud? What was the resolution roughly? You were saying about it.
This was a 4-channel system, so I think it probably had about 4 million, something like that. 4 million.
Divided by frame rate.
10 frames per second, maybe actually 20 frames per second. I can't remember. I can get the numbers for you, but maybe I would say, yeah, probably 20 frames per second and probably 4 million measurements. The 4-channel system, and we had 2 of them at 2 different angles.
Could you enhance your ability to do measurements if you added materials to them?
Say that again?
Could you enhance your ability to use it if you added different materials so that they?
Yeah, so the polarization information and the wavelength can be used to identify materials. We can use it for recycling and for other.
No, I meant even in doing that, if you want to, like, when watching the promotion, just like Hollywood will use dots and stuff. If you add something similar to that with different materials.
Yeah,
you
you could.
enhance basically your abilities to.
That's true. You could, yeah. Maybe you could. Yeah, we need to think about that. Yeah, we can discuss afterwards. Interesting. Yeah. So that's one. The other one is another promotional movie we did. This is against SiLC. She's having a discussion with her friends. It seems like
I think your speaker is attached to the owl.
oh yeah. Thank you.
No, I can't see the car.
Look, it comes 50 miles an hour towards us. Now 300 meters.
That car is too far. I still can't see any car. What car? I can't see. I'm blinded by the sun.
Wait! Stop, my friend. The car is approaching.
This car, Tesla. And I wish my LiDAR would have a SiLC vision chip like yours. I wish I had it too.
Okay, guys, I'll see what I can do for you. Ask us about our ionic vision sensor.
So SiLC represents how you can see the world much better than other robots can. Moving on, I mean, basically in summary, we are solving major problems in machine vision.
Getting back on this owl.
Yeah, I will use this. Thank you. We have a highly differentiated technology. We have a world-class team here, and we are very capital efficient. We have raised $67 million so far. Most of our competition has raised 10x us, and they have much less to show for it. I want to leave you with one last image of our city, Monrovia. This is a high resolution image of downtown Monrovia and the site. We're happy to send it to anybody who wants it.
I love it.
Thank you. So